Hello, this is Jack Jackson, and we're going to look at the topic of combinatorics, which are counting techniques. Now, we've seen that probability is a pretty easy idea. The basic idea for computing probability where the sample space is finite is very simple. Just take the size of the event and divide it by the size of the sample space. However, we've seen probability is easy, but counting is not always so easy. It's a little bit harder. We have to be real careful when we're counting these situations. Make sure that we're take into account if events are equally likely and so forth. And we've used several techniques to help us with that, including probability trees and contingency tables and some other things. But this idea of counting things is a little bit more difficult sometimes. And in this section, we're going to go over a series of videos here that are going to go over this special counting techniques that are called combinatorics. In fact, we're going to look at 6 different combinatorial techniques that are used for helpful in 6 types of situations. So the first one is what this video is going to be about, is the factorial. And this turns out to measure orders of distinct objects. So here's a problem we want to look at. Suppose there are 4 people with last names, just to make it easy, say start with letters A, B, C, and D. How many different single file lines can we make with these 4 people? What can we do to solve this problem? Well, one useful way of keeping track of all the options is to draw a tree diagram for the situation. We found this was helpful in things like the pair of dice problem or some of the other problems we looked at. So why don't you do this? Why don't you go ahead and make a tree listing out all the possibilities, and then we'll be able to count these up. Okay? Go ahead and do this. Press pause now. Well, if you've done this, you'll notice that for the first person in line, it could be the person with last names A, B, C, or D. But once the person A, for example, has been picked, the second person in line can't be A, but it could be B, C, or D. And say once A and then picked for the first and C for the second, then your only 2 choices, B and D, for the third person. And once the first, second, and third persons are picked, like for example A, C, D, then we only have 1 choice left for the last one, B. So basically we have 4 choices for the first person in line. For each of these, there are 3 choices for the second person in line. For each of those, there's 2 choices for the third person in line. And for each of those choices, there's only 1 choice for the last person in line. So if you see, I have listed all the choices here. A, B, C, D, A, B, D, C, A, C, B, D, and so forth. And if you count up all those choices, how many are there? Well, there's 24 of those choices. Okay, so how can we have seen this? Well, there are 4 choices for the first one. For each one of those, there's 3 choices, so that leaves 4 times 3 branches up to the second level. For each one of those, there's 2 for the next level. That's 4 times 3 times 2 for the next level, but only 1 choice for the last. So that leaves 4 times 3 times 2 times 1 paths or branches or orders altogether, which is 24 possibilities. Okay, let's do another situation. Suppose there are 8 different books on the shelf. How many different orders can we place these on the shelf? Now this time I'd like you to imagine the tree but not physically draw it and see if you can figure out how many this would be. Go ahead and work it out. Come back when you're ready. Press pause now. Well, hopefully you realize that say if you go left or right, there are 8 choices for the book on the left. And for every one you pick first, there's 7 different ones you can put next to it, the next one. And for every one of those pairs, there's 6 choices for the next. And then 5 for the next, then 4, 3, 2, and 1. So the answer would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And if you do that on your calculator, you get 40,000 320. Wow, that's big. It turns out that this just with 8 books, which is you know, maybe deceptively large, but it's true. That's how many it turns out to be. And you can see why I didn't want you to physically actually draw out the tree. That's a pretty big tree. But hopefully you can kind of imagine it out there anyway, right? 8 branches first, and each one of those goes 7, and each one of those goes 6, and each one of those has 5, and so forth. Well, this leads us to defining a function that's useful here, and it's called the factorial function. Now, just for our purposes of making this work, we would like to define 0 factorial to be 1. So n factorial is 1 if n is 0. 0 factorial is just defined to be 1. And then what we do is we let n factorial be the product from k equals 1 to n of k. Now, this product notation, capital pi here, not the lowercase pi, which is the circumference of a circle divided by its diameter, a number, right? This capital pi is kind of like a summation symbol. It means take this number, this thing, evaluate it at k equals 1, evaluate it at k equals 2, k equals 3, all the way up to n, and then pi is like a p for product, just like a sigma is like an s for sum. So what this symbol means is take this formula, evaluate it at k equals 1, k equals 2, up to k equals n, and then multiply them. So this is just a shorthand notation of this. 1 times 2 times 3 times 4 times 5 times 6, all the way up to whatever n is. Now we had them written backwards when we were doing it before, so you could also write it as n times n minus 1 times n minus 2 and work your way down to 1. But either way, you get what we call n factorial. And this second line here is defined for any natural number n, and since we throw in n factorial is 1 if n is 0, we have factorial is now defined for any whole number. Notice we also have a recursive pattern that n factorial is n times n minus 1 factorial. And by the way, there's an order of operations here too. The factorial takes precedence over the multiplication. And it turns out that n factorial is exactly the number of ways of permuting or placing in order n distinct objects. So without a calculator, let's work out some of the lower values for the factorial function. So starting at the beginning, write these down. What is 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5 factorial, and 6 factorial? See if you can work these out now based on the definition we just did. Press pause now. Well, you don't really even need a calculator to do this. By definition, 0 factorial is 1. 1 factorial is also just 1 by the definition. 2 factorial is 1 times 2, or 2 times 1, which is just 2. 3 factorial is 1 times 2 times 3, which is 6, but you could also think of it as taking the 2 that's up here for 2 factorial and multiplying by 3, and that's 6, either way. 4 factorial is 1 times 2 times 3 times 4, which is also just 4 times the 3 factorial, so 4 times 6 is 24. 5 factorial is 1 times 2 times 3 times 4 times 5, or if you'd rather, 5 times 4 times 3 times 2 times 1. And notice that that's just 5 times the 4 factorial. The 4 times 3 times 2 times 1 is the 4 factorial. So that's just 5 times 24. We can do that in our head. That's 120. 6 factorial is 1 times 2 times 3 times 4 times 5 times 6, which is just 6 times the 5 factorial, or 6 times 120. That's 720. And so we can build it up like this. And of course, the next one we could get 7 factorial would be just 7 times 720, and so forth. So we don't really need a calculator to do these if the number is pretty small, and if we're allowed, take our time and build it up. But luckily, there is a calculator shortcut for this on your calculator. So if you're using a TI-84, here's how you get to it. You just, in both cases, on a TI-84 and a TI-Nspire, you type the number and then the exclamation point, which is a factorial symbol. And the way you do that here is on the TI-84, you hit math and then do probability number 4, which is the factorial. So if you want to do 6 factorial, for example, you type a 6 first, then you hit math, probability 4, and that gives you the factorial, and hit enter, it's 720. On the TI Inspire, it's very similar. You're at their home screen, you hit menu, you go down here to number 5, probability, choose factorial, which is number 1. You needed a first typed in your number. So for example, if we want to do 5 factorial, we hit the 5 first, then we hit menu, choose number 5 probability, and number 1 factorial. You could actually hit menu 5-1 if you wanted to, or you can do menu and then use your arrow keys to get the rest and get over to here and hit enter. And so we get 120 just like we calculated. Okay, so use your calculator now and figure out these values here. So instead of doing these by hand, use your calculator. Find 10 factorial, 15 factorial, 20 factorial, and at least approximately 69 factorial and 70 factorial. Go ahead and do this now. Press pause. Okay, well, here they are right here on the TI-84. 10 factorial is 3628800, or 3,628,800. 15 factorial switches to scientific notation, so it's approximately 1.3 times 10 to the 12th power. So that's 130767436, and 3 more digits. It turns out the other 3 digits actually are 3 zeros. We know that because they're below 15, we've got 15, 5, and 10, which are all multiples of 5, and you've got a whole bunch of multiples of 2. So you're going to have at least 3 multiples of 10 in that product. So this is going to be a multiple of 1,000. If you do it on the Inspire, at least the Inspire Cast, and I think the Inspire Non-Cast does this as well, I think, you're going to get all the digits worked out in regular notation here. 20 factorial works out this exactly, and of course this approximates it here. This one actually is rounded off in the 20 factorial. It's about 2.432902008 times 10 to the 18th. It's exactly 2.43290700817664000. So if you can see, it sort of dropped it off at the 8 here, ignored these, so it rounded off there, and then put it in scientific notation. But I got the exact value out of the Inspire. 69 factorial, here it is. If I arrow over, I can get all the digits here on the Inspire, but I'll just round it off like the calculator did on the TI-84. It's about 1.7 times 10 to the 98th. But look what happens on the TI-84 when you press 70 factorial. It just gives you an error message. It actually says error overflow, and if you quit, it'll go back to here and just say error. So basically what's happening is if you see here on the TI-80 or the TI Inspire, and you see all the digits written out, if you put this in scientific notation, it's about 1.198 times 10 to the 100th power. Well, the TI-84 doesn't do anything bigger than 9.99999 times 10 to the 99th power. It won't do exponents above. It won't do powers of 10 above 99. And so what happens is the number just got too big for the TI-84 to even handle it all. So it's really remarkable how fast this function grows. You may be used to some other functions that grow fast, like some big power functions. Exponential functions grow faster than that. Well, factorials grow even faster than that. So the time we're up to 70 factorial, it's too big for the TI-84 calculator to even work with. So that's kind of interesting there, but we can use it to the calculator to at least approximately work these out for the bigger ones and exactly work it out for the smaller ones. All right, so using this information, see if we can solve these problems. If there's a collection of 11 books, let's say they're each by a different author, How many orders can they be arranged on the shelf? And then how does this connect back to probability? Well, if an arrangement, one of these arrangements is selected at random, what's the probability that they will just happen to be in alphabetical order of the author? Okay, you should be able to figure this out now based on what we've done. Press pause now. Okay, and you're back. Hopefully you've worked it out yourself. If you haven't, go ahead and do that and come back. And here's what we get. Well, there are 11 factorial different orders that we can put them in. And we can see actually that works out nicely on the either calculator, an exact value, 399,16800. You get the same thing, exact value both. So that's 39,916,800 different orders. Wow, just with 11 books. Counterintuitive, isn't it, a little bit? Sometimes it doesn't seem like there should be that many possibilities, perhaps, but there are. There's a lot, and we've seen that that's the truth. If an arrangement is selected at random, what's the probability of being in alphabetical order? Well, alphabetical order is only one of those over, nearly 40 million choices. So the probability exactly is 1 over 39,916,800. Or if you do it in decimals, that's approximately let's see, should be 7 zeros and a 2. Let's see, count up, see if I got it the right number. 1, not counting the 1 in the front. 1, 2, 3, 4, 5, 6, 7 zeros, and then 25052, at least to that many significant digits, or about 2.5052 times 10 to the negative 8th power. Okay, so that is the factorial function, and it's used to count the number of orders you can put, distinct orders you can put in distinct books that are in distinct objects in general, and that's in factorial.